for polynomial type problems.
How does P how is P automatically inside NP?
So we don't know if there's anything that's in NP that isn't in P. So P could be equal to NP. We don't know.
What's the justification that there isn't anything in P that's outside of it, or that's inside P but outside of it?
So NP by definition is you can check the answer in polynomial time given some advice. Things in P, you get the answer in polynomial time with no advice.
But so that's like that implies that checking what is the notation? That solving necessarily takes equal or less time.
Solving given no advice takes equal or greater time than solving with advice, which should be clear. Yeah. Yeah.
No, that's crazy.
All right, I already passed 4, so I should get started. Hello, everyone. Thanks for coming on a Friday. You're rewarded with a quiz, so enjoy. We're going to start with a little bit of a recap. So hopefully all of you got it decently last time, but we're going to talk about it again, and we're going to get to do some of the interesting stuff here. By the way, also, everyone is now done with the exam, so if you'd like to ask me any questions about the exam or ask for any answers, I can now give them to you, just so you know. If anyone has any really pressing ones, I can do that now. Okay, cool. All right, oh, one more thing. I forgot to levy this challenge to you guys because the weather's been bad. What I offer each of my classes, if anyone is able to beat me in tennis, I will actually give you bonus stars. Hasn't happened yet, Anyway. So, back to these. So we had these complexity classes. As a reminder, this is ways that we could group problems. This is how we group the difficulty of different problems, the sort of intrinsic difficulty of different problems. In particular, we cared about problems that only we had to answer yes or no to. Those are decision problems. And we had 3 classes that we're going to really care about in the rest of this class, which are P. This is all of the problems where there does exist a polynomial time solution to solve the problem. Cool. Then there is non-deterministic polynomial time, NP. Can someone remind me what NP is? Yeah. Yeah, so could you solve the problem in polynomial time on a non-deterministic machine? That is a non-deterministic Turing machine. Another way to formulate this is if I'm given some piece of information, sometimes called a certificate, can I return the answer yes correctly in polynomial time? So you'll notice that there's these two groups, NP and co-NP. Problems in NP, we are able to verify in polynomial time if we're given this certificate. In co-NP, we're able to say that they are false given the same information. Okay? So we're able to show that the solution is false if we're given this certificate of information. Okay? Do those make sense? Generally, the format for us to prove that something is in NP is we'd like to take the problem, say, here is the information I would give my solver, and then like here is the certificate if you prefer that verbiage, and then here is how I would then solve the problem in polynomial time. Here's how I would verify that solution in polynomial time. Generally, in this class, just because it's a common thing, we're going to give the solution to the problem as our certificate, but it need not be that. It can be any information that is polynomial space, polynomial time to read, I suppose. Okay? That makes sense? That makes sense? We also noticed that all of the problems that are in P are also in NP. I will remind you sort of a different way we could phrase what P is this is the problems that we're able to decide both if it is correct, if it's true, and also if it's false in polynomial time with no advice on a Turing machine. So you can imagine that the NP class, that is the problems that we can solve in polynomial time if given advice, are strictly or equally more difficult than the ones that we can do in polynomial time with no advice. Does this make sense? One other way we can visualize this is that we have concentric circles. Now, what do we know about the things in this area between P and NP? Yes?
P is fully inside it.
So we know that P is fully inside NP. We do know that. So P is certainly a subset or equal to NP. This is a known fact. But what about things that exist in this realm? Things that are in NP but not in P? Yes?
There may not be not in P.
Exactly. We don't know if there exists anything in this region, in any of these three regions. We don't know. We do know that there exist things that are in exponential time that are not in these. We don't know if there is anything in these three groups here. Okay? So today we're going to talk about how you might be able to prove that something is in there or not in there, and also how we can define what is an interesting concept of the hardest problems that are in those sets. Okay? All right, any questions on this hierarchy at all, or the definition of NP or co-NP? Anything? Yes? So it is, so certainly all of P is in both of them, is the first thing. So these problems here, right here, which are the intersection but not in P, would be problems that are not solvable in polynomial time, but given advice, you could both prove it true and false. Yeah, that'd be what they would be. And again, there is no known problem in there with all of these. Yeah. So the question remains, it's still an open question. It's been an open question for a while now, but probably someone will figure out eventually. It is unknown if P is equal to NP. One of you guys could very well be the ones to solve this, actually. It's about time for that. Someone can do it. Okay, so now we're going to define one new class, or really two new classes that we care about. Where did I leave my blue marker? Pocket, of course. We're going to have, I'll use red actually for this. We're going to have a new class which is going to be inside of NP. By the way, this is not outside of NP. We're going to have a new set of problems right here, and these are going to be the NP complete problems. Okay? And these problems are going to be the hardest, we'll talk about what that means in a second, problems in the class NP. And likewise, we're going to have another set here, which are going to be co-NP complete. Generally, by the way, we tend to just talk about this set. Most of the problems that are here, we could just invert the question, and they would end up here. So that's the relationship between some of them, although there are some that are better to think of as co-NP versus as NP, but they tend to be the same problems. Yeah?
Is NP complete?
Yes. So we will explain that in a second. To answer it briefly, there is this other class called NP hard, and those are going to be all of the problems that are harder or equally as hard as these problems. So it would include everything out here. So that would be everything in this bubble here would also be considered NP hard. So NP hard would be everything harder than NP and everything NP complete. We'll talk about NP hardness in a little bit. In fact, we're about to get to that. So this set is very difficult for us to find anything in to start. We need to somehow contrive a problem that is harder than this entire set of problems, which is effectively infinite. There's some infinite number of problems here, and I need to show that I have a problem that is strictly harder than the rest of them. So we need to develop some tools. Okay. Firstly, I'm not going to cover this proof fully. If you're interested in it, there is a cool proof, but it's a little out of scope and it's a little bit difficult to do in lecture. But the first thing we're going to do is we're going to prove the existence of one problem in this set. Okay? So we're not going to fully prove it, but I'm going to describe the problem to you and give a hand-wavy proof as to why it is the hardest problem. Okay? So this problem, our canonical first NP-complete problem, is going to be called circuit sat. Circuit sat. What this problem is, is given a digital circuit, like an analog circuit even, so that is made of ors, ands, and nots, however I'd like to. You can think of this either as a formula, sort of like, you know, x and y or z all knotted, like and whatever. We can, or whatever. Like we can have whatever expression we'd like that. You can also think of it as an actual digital circuit where we have all of our different inputs and we have our gates, and we would like to know after our entire circuit if there exists any assignment of these variables, that is either these x whatever's xi's or xyz, etc. Is there some assignment that is true and false assignment to each one of them such that the entire expression resolves to true? We want to know, do any of those exist? Okay? Any questions on the formulation of that problem? This is an important one to understand, by the way. We're going to be talking about this basically the rest of the class. Yeah?
Just to clarify, we're trying to find the
We're trying to find a setting of all of the variables simultaneously such that the entire thing resolves to true. And we only care about, does one exist? We don't even need to find it necessarily. This is a decision problem. Now, first question to all of you, is this in NP? Okay, why is it in NP? I got some thumbs up, some quiet thumbs up. I think, did you say yes? Why is it in NP?
Because you have a solution, it's super
Yeah, exactly. So it's in NP because if we get an assignment, that is our certificate here saying, here is a satisfying solution to this formula, then I can plug it in and I can resolve it in polynomial time, right? Yeah, so by doing that, I can show that this is in fact in NP, and now the secondary thing I need to show is that it is more difficult than every problem in NP, which is more difficult or as difficult as every problem in NP. Any ideas how we might do this? Yeah. Has the highest time complexity. It would be, I mean, the problem, determining what time complexity is absolutely necessary for a problem is very difficult, actually. And the set of problems in NP is not fully known. We don't know every problem in there, and it's difficult for us to say all of these problems are under this time complexity, although we have a loose bound on it, but we don't know exactly what it'll be. So not exactly. It's a reasonable thought, though. Any other ideas? Yeah.
space complexity.
Still not space complexity. Space complexity does end up mattering some amount, but it won't be how we're going to go about doing this. There's I suppose, less consistent from what we've talked about with analyzing algorithms before, but there's a very natural way for us to think about comparing different problems. We've done this a little bit in class before, but you may not have realized what we were doing. So what we're going to do is we're going to show, let's take some arbitrary problem first. So let's take some arbitrary NP problem before we try to do this for all NP problems. Is slightly more difficult. What I want to say is that if I have an instance of some problem, so as I have some problem A, I'm doing a little erasing so I have some space. Actually, everyone can see here fine, right? I'm just going to write it here. So if I have some problem A, so given an instance of problem A, of some arbitrary problem, I want to show, let's say I'll label lowercase a. I'll label that lowercase a just so I can keep my notation consistent. What I want to do is I want to find some way to translate that problem into an instance of this problem. So this is for every instance of A, I would like to have a function somehow such that I'll say such that circuit sat evaluated on that translated version of the problem. So if I can translate it somehow, so this is some function f, I'm translating some instance of this problem into a version of the circuit sat problem. That is, no matter what my input A was, I'm turning it into a circuit. I'm turning it into a circuit, and I would like it to be the case that this now being evaluated using circuit sat, so the truth value of the circuit sat is equivalent to the truth value of A. So that is problem A evaluated on instance A. Bit of a weird notation, but I'll stick to it. I'm saying, if I have some problem A, right? Let's say that this is finding the longest path of a graph, let's say. Then, if I am able to take any arbitrary instance of that graph problem, translate it through some set function that I have to design into being a circuit, such that if this circuit is satisfiable, that graph has a longest path of length k, right? So if I'm able to do this and show that both directions, both if this is true, then this is true, and if this is false, this is false. So I have to show that they are equivalent, okay? Or true, true, false, false, yeah. Any questions on this? So this, yeah? So this is called a reduction. So this is called a reduction, and the way we would denote this, if I'm able to prove this fact, if I'm able to prove that there exists some f such that all of this is true, then I say that A reduces, we use a less than equal sign because it's very appropriate here, reduces to circuit sat. I was just going to write circuit because I don't have space. So this would mean that I have reduced A to circuit sat, and in fact, we can now say, we can just about say, that circuit sat is a more difficult problem than A is. Because if I'm able to take every possible instance of A, turn it into a circuit sat problem, and solve it using circuit sat, then clearly it can only be as difficult as circuit sat. Asterisk. Anyone, can anyone tell me what the asterisk is here? Sure. So this is exactly the point. What if I choose my f, let's say my f will evaluate whether or not it will return a true with A. So I can use, let's say, exponential time to just solve the problem, A, and then have my thing only output a circuit that will output true if A should be evaluated to true, and false if A should be evaluated to false. That is, if I allow this function to take an arbitrary amount of time, I can just solve the problem. And in fact, this reduction means nothing now. It's a meaningless statement if I allow f to be whatever. So we make one notational change and one conceptual change, which is adding a little p here. And this is now going to be a polynomial time reduction, meaning that all of this process, both, I guess the main thing of this is translating A into f of A, can only take polynomial time. And we can see, again, because all these problems are more difficult than polynomial time, or as difficult or harder than polynomial time, we know that it isn't a problem to the runtime of these algorithms themselves. So, if I'm able to do this, and if this only runs in polynomial time, then we do, in fact, have it. That means that if we have all of these components, we have so we have circuit sat is in NP, and we have that there exists some translation in polynomial time from some arbitrary problem A into this, then we have that A is reduced to circuit. And I've been hinting at here a little bit, we're going to be able to say this for any problem A. That's what we're going to be able to do with circuit sat. Now, this part of the proof, where I show that any problem A can be reduced to circuit sat, is a bit finicky and a little bit annoying. I'm going to give it to you at a high level. We're going to have actual proofs later on in the class, so don't worry, we'll have a little bit more actual reductions. This one's just a little bit dense. But the high level information of it is basically that there exists a polynomial time translation from any algorithm, which is a specifically defined object in theoretical computer science, but an algorithm we can then convert into a circuit in polynomial time. So we'll end up being able to convert all of our algorithms to solve all these other NP problems into a circuit, and then evaluating the circuit's trueness or falseness will be equivalent to just evaluating the original problem. Do we understand the high level of that? Basically, I can just turn any computer code into a circuit, and then the circuit can solve it. So this is going to be my reduction from any arbitrary problem A, or any arbitrary instance of an arbitrary problem A. I'm going to convert it into a circuit in polynomial time. There exists a way to do this. We don't need to worry too much about that. Yeah?
Well, more specifically, it's an NP problem.
Yeah, it was saying every NP problem. Yeah. Not every problem that exists, obviously. Just every NP problem can be converted into a circuit in polynomial time, and then will be evaluated in the same truthfulness. Yeah. If it was every problem, then of course I could do this with exponential time and show that circuit sat is arbitrarily difficult. But it is in fact only NP. Okay. Does this make sense to everyone? Okay. So what we'll end up having is that circuit sat is going to be greater than or equal to every single problem in NP is going to reduce in polynomial time to circuit sat, and we have that circuit sat is in NP, and so it must be the most difficult problem in NP. Do you understand this logic? Okay. Any questions on this before we continue? Yeah. Right here? Yeah. So I'm saying that these are two different ways to represent what a circuit is. Oh. Yeah. These, by the way, do also allow arbitrarily many inputs to ands, ors. Not has to be a unary operator, though. Just so you know. But yeah, any problem can be converted into this format in polynomial time. Any NP problem can be converted into this format in polynomial time, and then we can use a circuit sat solver to solve it. One other way you can think about what a reduction is doing, by the way, a visualization that I happen to like, is you can imagine that we have a little bubble here that's going to represent all of the instances of some problem A. Okay? All the possible instances of some problem A. And then we have some other problem. Say this, let's call this problem B just for now. This would be circuit sat in our proof before, but I'm just going to call it B. And what a reduction is showing is that every instance of this problem, the entire set, can be translated with some function f of A here into some subset of B. It doesn't need to be a strict subset. It could be the entire set. And in fact, we're going to see that there are several problems where this can be done in the reverse too. We can reduce all of B to some subset of A, and that will show that they have a one-to-one relationship. And this diagram here is that A reduces to B in polynomial time. Okay? Almost every person who learns this at some point messes up the ordering here. I'm going to try my best to try to get you guys to get it the first time. Which is I'm showing that A is smaller than B, right? That's pretty obvious with this notation, saying that it is an easier or equally difficult problem. And the reduction is read left to right. So A is being reduced to B. Make sense? So I'm taking A and I'm reducing it to some subset of B, and then I'm saying I could use a B solver to solve A. Make sense? After some examples, I think it'll become more natural, but hopefully it will come quickly, all of you. Okay, so far, we have exactly one NP complete problem, which is circuit sat. Oh, I also forgot to mention this property, that every problem of NP, every problem in NP can be reduced to some problem, is the definition of NP hard. So we're asking before what NP hard is. It is if every problem in NP, so this is for all instances of A, so this is for all A in NP. So if for all A in NP, and then all instances of every problem in NP, I can do this reduction, then I get given that circuit sat here is NP hard, is in NP hard. It's another class. Okay, cool. And the definition of NP complete is exactly that it is NP hard and that it's in NP. Those two things combined gives us NP complete. Okay, make sense? I'll write that somewhere here. So NP complete is equivalent to the intersection of NP and NP hard. Make sense? You put your phone away. I'll pocket it even. It's distracting me. Okay. Yeah, question.
Just for clarification, does that mean everything in NP complete has equal difficulty?
So what it means, I think, again, thinking of it as a strict hierarchy of difficulties, maybe not as much. But if I have a problem that is NP complete, in fact, I'll save this for right now. What we're going to do now is we want to find a second problem that is NP complete. And luckily for us, the second problem is much easier to find than the first problem. Anyone know why? Yeah.
Because we can just show the
Exactly. What we can show,
problem reduces to that problem.
we can show that circuit sat reduces to some other problem. I'll just write what it is. It's going to be 3 sat. So if we show that some other problem, or that this now most difficult problem also has a reduction to something else, why does this make sense that this would show that that is also NP hard? So I'm using a less than equal to sign, which implies that it's transitive, but it's not necessarily immediately obvious that it is. So why is it that this is a transitive operation? Why is it if I have that this is greater than equal to all of NP, right? Then how come if I reduce that to 3 sat, then I have that this, because this would have to give me as a property that all of NP reduces to 3 sat. So why is that the case? Yeah. Exactly, we just chain the reductions together. So if I have some function f that converts some problem into circuit sat, and then I have some function g that converts circuit sat to 3 sat, then I can just say that I have some new function that is the composition of f and g, and that would work. Yes?
Sorry, is NP hard?
No, the intersection of it is NP complete.
So there are
There are some, yes, of course. So everything that is more difficult than NP, that is strictly more difficult than NP, is also, there would exist a polynomial reduction to any exponentially hard problem. Yeah. Yeah. Yes?
So we're assuming
We will show that momentarily. Yeah. Yeah.
This relies on the fact that like the polynomial of a polynomial is still a polynomial.
Yeah.
So like when you do like translate the thing, it's like
Yeah. He's pointing out that the composition, when I said I had some function f and I had some function g here, knowing that f of g of, or other way around, g of f of a is also polynomial is relies on mathematical fact. That is not necessarily obvious that that would be true, because I could have exponential, or I could have a polynomial blow up, and the polynomial will blow up again. Maybe that's exponential. Turns out it isn't. If we do polynomials of polynomials, we get polynomials. Anyway. So let's look at 3 sat. So 3 sat, let's define the problem first, and then we'll talk about how we do this reduction and how we can prove it's NP complete. So 3 sat is the following problem. Let me switch to blue. So this is our goal, is we'd like to show that 3 sat is NP complete. The problem, 3 sat, is as follows. We are going to have a circuit. Once again, circuits end up mattering quite a bit in all of this. But these circuits have a limited properties. In particular, they are built of clauses, is what we're going to call them, that have 3 elements or fewer. We're going to start with that because it's an easier proof, but it could be exactly 3, is fine. There's a different, don't worry about that. We're going to say 3 or fewer elements in each clause. So it'd be something like x0, and then we're going to be ORed together. So it'd be x1, and let's say x2. Okay, so this would be a single clause. So this is I'll label them with red to maybe not clutter it. So this is a clause, and each of them is going to be ANDed together. So we're going to have multiple of these ANDed together, and inside of these, I can have repeats. So I can have that x0 appears in this one again. I could also have that, I'm going to erase this real quick. I could also have that, hopefully we're all good on this diagram. It's not too complicated. We can also have that we have knots of them, and they can also not be totally overlapped, of course. I can have some xi or whatever, and we're going to have n of these. So we're going to have n clauses with 3 elements each. And now, this format, by the way, that we have here is called CNF, or conjunctive normal form. So these clauses are being conjoined, that is, they're ANDed, right? Conjunctive normal form, okay? So this whole thing here is called, this format is called CNF, conjunctive normal form, CNF, running NP, CNF, and this is 3 CNF. So this is, all these are in 3 CNF. And again, I'm going to do this somewhat briefly just because it's not particularly enlightening. But what we can find is that we're able to, here, I do have this here, so I'll do it a little bit. Let me erase this. What we're going to be able to do is we're going to be able to come up with this function f. So remember our overall objective. I'll actually probably write the definition of a reduction elsewhere explicitly. But I would like to create some function. I guess first let's prove NP. So first, is this an NP? That is, if I give you a piece of advice, am I able to solve this in polynomial time? The answer is yes. It's very similar to the SAT problem. If I give you the solution, you can verify that the solution is correct in polynomial time. Yes?
Okay, so I wanted to ask a question.
Yeah.
How can NP complete be
NP hard cannot be reduced to NP. NP hard is the set of problems in which all problems from NP reduce to it. So that is, okay. Now I'll write some definitions over here, actually, just so we have them on hand. These definitions are important, and you'll use them, so it's worth having them. So, NP hard. So I'll write it as a definition here. One sec. So say that some problem A, I'll use A here. A is in NP hard if and only if for all problems in NP. So I'll use some other letter. I'll say B in NP. There exists some reduction B reducing to A. Okay, so that's the definition of NP hard. Okay. NP complete are problems that are NP hard and are in NP themselves. So again, over here, NP complete is equivalent to this. So I'll write it here also. So A is NP complete if and only if it is in NP hard and in NP. Cool? Yeah.
So if all of them
Reducing NP hard doesn't mean anything. So NP hard is the set of problems that satisfy this property where there's a reduction from all problems in NP to it. So they are problems that are as hard or harder than every problem in NP. It's a set of problems like that. Cool? Cool. And then when I say this means that both it is NP hard, that is, everything reduces to it, everything in NP reduces to it, and also it is in NP itself. Is what we say is NP complete. Okay? There's a similar notion, by the way, for P. There is, in fact, a group called P complete, and you can do something similar there. But NP complete is a much more interesting group. All right. That okay? Okay. So let's get back to 3 sets. So first off, it's in NP pretty obviously. And then we need to prove the following. We need to prove that for every instance of circuit sat, I'll say circuit, I'll use C. So for every possible instance of circuit sat, I guess I'll say there exists some function. Exists some function such that for every possible circuit of circuit sat, we will have the following. If we do circuit sat on that circuit, if I evaluate whether or not that circuit is satisfiable, that'll give me some answer, and that answer has to be equivalent to the answer that I would get from doing 3 sat on my translated problem. Okay? Does this make sense? This is the definition of a reduction. So this is exactly the definition of a reduction from circuit sat to 3 sat. So this is exactly that definition, is this. Okay? Does this make sense to everyone? I want to make sure it's a topic that I think is easy to be slightly confused on, but hopefully it's making a lot of sense. So these two things are equivalent. There you go. And these two things are equivalent statements. Okay. This is pretty clearly in NP. Now, how can we do this reduction? Any ideas? Yeah. More or less, yes. I'll give you a specific example of this. So we can imagine in our circuit, if we have the following, so say this is an actual circuit here. Let's say that we have, let's start with a NOT. NOT should be somewhat easy. So for every one of the elements in our circuit, right, there's a NOT gate. We'll say that we have some input, I'll call it X and Y. So some input, let's say X, some output Y, and we have we can say that if this appears in our circuit, then we have the logical fact that Y is equivalent to not X. Okay? And it turns out that this, in fact, can be expressed in this form. Make sense? So this I can now express, this is my translation function f here. This can be expressed, I'm going to do this one for you. I'll do 2 of them, and then I'll give you the chance to do the last one, see if you got it. So this is going to be translated into my 3 sat format, and it is going to be the following. It's going to be not X or not Y, and X or Y. Yeah, that makes sense. Okay? So you can realize that if this is not satisfied, then this would never be satisfied. So this, yeah? So I defined 3 sat earlier. It's fair to say it isn't. We can add elements very easily. So you can adding an element, I would just do this. I would say like that. That is an equivalent statement to this one. So I can always increase the number up to it. It's a small detail here, but if I would just allow it to be like this, it removes that detail. Yeah, so this would technically be at most 3 sat. And in fact, you can show that at most 3 sat very quickly. You can show that it reduces to 3 sat. So 3 sat is going to be the problem that we're overall reducing to. Anyway, so this would be a NOT gate. Okay, this is how we translate a NOT gate. Then we can look at how we translate something like an AND gate. Okay, so we had an AND gate. Then I'd say I have like x0, x1. And each of these go through and makes, I'll do y again. And this would be saying that y is equivalent to x0 and x1, right? Make sense? And we can apply our logic rules. If you're uncomfortable with these logic rules, not tremendously important right now, but you should probably brush up on them. SAT is something we're going to see a lot of, and it's one of the most canonically important examples for NP completeness proofs. And you probably are going to have to do reductions with SAT. So it's probably going to be nice to be comfortable with it. This is going to end up being equivalent to, give me a second to write it up. It's going to be equivalent to y or not x0 or not x1 and not y, I do actually know it, not y or x0 and not y or x1. Okay? So it's going to be equivalent to this. You can take a second to confirm this with yourself. It is true. If you don't want to confirm it right now, then perhaps you can write it down and confirm for yourself later if you'd like to justify that to yourself, but it is in fact true. Yes? What do you mean one clause? It's like... Mm-hmm. Well, that won't actually help us here. So if I did like x0 and x1, right? I guess sure. That wouldn't. Right? So the problem is I need to have this statement said. I don't want a thing that is x1 and x2. That might be true, might not be true. But this later on I could not or something. Like it doesn't necessarily mean that I want this like this. Anyway, why don't you all attempt or, by the way? Give it a little try. This will be a little bit of practice. I'm just going to give you like a minute or two because I do want to get to the actual meat of the class today. Yeah. In what? Just and x0 and x1? Like, you're saying this, right? You're pointing this? This? What about it? Or them? Oh, you're saying to do the or one. So you do that, and then you have to change it here. Yeah. Like, we're caring about making this.
You just want to try it alone.
So you're just doing the same process of saying, if I were to have an OR gate in my actual circuit, how would I translate it to 3-sat form? Yeah. Okay. For the sake of keeping things moving a little bit, I'm going to not give you too much time on this. Anyone figure out a quick way to do it? There's a very quick way to do it. Yeah? Okay. Something you could realize hypothetically is that and is, so A and B is equivalent to not A, or not B. So what you can do, in fact, is just invert all of the knots across here. Because we're going to do the y is going to be knotted, and then each of the elements is going to be knotted, and that would convert it. That's maybe something that is difficult to reason out quickly. It's okay. But we would just invert all of these. So if I did or, I would just flip all of the knots in this entire thing, and that in fact would be x0 or x1 is equivalent to y. Okay? Okay. You can just believe me, I suppose, that from here, the main interesting part of this reduction is we can take our entire circuit, label each of the outputs of each of the operations like so, sort of how we did with the computation graph, and then do the same thing with each of them. So each operation will only give a polynomially large expression in 3-sat. We can actually say that, in fact, if I have an arbitrary number of inputs here, it still will only be polynomially long. In fact, if I add terms to my and, it will only add one clause per plus one element to this clause, which I can then break up into multiple clauses for 3-sat. Okay, so what we can do is we take our entire circuit, we do these conversions. Each one of these only takes polynomial time, and there is only a polynomial number of them. Therefore, our final CNF thing here we can create in polynomial time, and it is only polynomially large. Okay? Does that reasonably sit well with everyone? So if I have an arbitrary circuit built out of these operations, I can convert it into CNF in polynomial time. That's the punchline. The way we got about it is a little bit more logic heavy, but we can get there. Okay? And I am hand-waving a little bit of this proof just because it's a little bit tedious. Okay. So then this here we can now solve, and if I solve this CNF, I've shown that these two are equivalent. So if I solve this and I get a true statement, if I say it is true, then that means that I can also say that circuits at the original circuit would also be evaluated to true, and vice versa. Okay? So that's a relatively straightforward reduction. I'm converting a circuit into a circuit. Not too bad. Not too bad. I know it's a little bit involved if you don't like circuit logic, but it's a fairly straightforward reduction. Okay. Any questions on this? I'm going to ask you, so we have, inadvertently, we've proven that any circuit at all can be written in CNF form. It turns out they can also be written in DNF form, which is the following. DNF form is the opposites, basically flip the ands and the ors. So DNF form is a good term to know, by the way, but I'll talk about why we don't talk about it too much. So DNF form would be the following. This is disjoint form. Is going to be the opposite, so it would be something like x0 and x1 and x2, or, and so on. So we can also have the fact that any circuit can be reduced to either one of these forms. That's just a fact that I'm going to give you. Now, the question is, how long would it take to figure out if a DNF formula is satisfiable? Yeah? So I'll point out that each of these is just ORed together. Okay? So if this first clause is true, then the whole thing evaluates to true. So all I need to do is check each clause to see if it has a contradiction, if it has xi and not xi in it. As long as at least one of them doesn't, then it's satisfiable. So now the question I'll ask all of you is, if something like this exists, and I promise you that every circuit can be converted into this form, how come circuit sat isn't polynomial time? How come I can't just instantly say circuit sat is polynomial time, p equals np, I'm happy? Any guesses? Yeah. Exactly. The conversion takes exponential time, in fact, provably exponential time to convert from an arbitrary circuit into DNF form. So it's an interesting bit of niche here where this is an example of why we need that restriction. But DNF form is much less useful for that reason, because we can't just arbitrarily convert things to DNF. We can, however, convert them to CNF if we'd like to. So anytime we have a logical statement, we can convert it to CNF form. In fact, if we have any algorithm at all, we could convert it to CNF form if we so chose. Okay, so let's now look at a slightly more involved reduction. So slightly more artistic reduction, I'll say. So I'm going to introduce a new problem. So if you don't, if you need any of this, take a picture right now. I'm erasing it right now. We're going to talk about a graph problem. So we've talked about circuit problems a lot, and perhaps you don't like them. Luckily, there are a lot of other types of problems. So let's talk about a problem called independent set. The problem is as follows. Given some graph, I want to show if there is a subset of nodes. So let's say I have some graph. Whatever, some arbitrary graph. And I want to know, does there exist, so we have some graph, the input to this is going to be a graph, which is going to have vertices and edges, and is also going to be some number, I'll call it k here. And the question is, does there exist does there exist some set of vertices, does some subset S, which is a subset of V, does some subset exist such that the size of S is equal to K, and there does not exist, there does not exist any edge out of all my edges between two elements of S. Okay? So that is, there's no, okay, 1 second, sorry, I'll write the logical formula properly. For all pairs of elements in S, there does not exist any edge in my set of edges such that there's an edge from S1 to S2. Okay? I wrote it all in logic here, but this is basically saying if this node here is in S and this node here is in S, then that's no longer an independent set because they share an edge together. So if I said here for this problem, if I said this is my graph and my K is 2, then is it true or false? It's true because I can mark these two right here. But if I said if K is equal to 3, is it true? It is not. There's no third node I can mark, no other way I can do this, such that none of them are neighbors to each other. Okay. So now, for all of you, we want to convert 3-sat into this problem. We'd like to show that this problem, independent set, is NP complete. Okay. First off, is it an NP? Is it an NP? Yeah. It should be fairly easy. How could we check it? We can check it just by giving the solution once again, and then making sure that none of them are neighbors and that there are k of them. As long as we both those checks pass, then we say it's good. Cool. Now, the reduction, the more difficult thing. So I'm going to say that I want the reduction from 3-sat to independent set. Independent set. How might I go about doing this? So first off, what am I converting into what? If I'm trying to do this reduction. So I'm converting 3-sat into an independent set. That is, I want to take an arbitrary circuit and turn it into a graph plus a number. Okay? So let's say that I have some arbitrary circuit now. So let's say that I have some circuit here. So this is my 3-sat instance. It'll be something like x0 or x2 or not x3, and it would be let's say not x0 or not x2 or x4, something like this. Okay? Let's say this is my circuit, this is my input. And I'd like to somehow convert this into a graph and a number such that if this is satisfiable, this will output true. Any thoughts? Can you slap his phone really hard? Thank you. Okay, any thoughts? Okay. This is not one that I intend for you guys to solve, by the way. The one that I've given as a quiz, I do intend you to solve. This one requires a little bit of artistry, and this is what we're going to see with a lot of reductions. I'm going to talk about a couple components we see. First off, when we're doing reductions from 3-sat, generally we want to find a way to convert a clause into something, right? And what we're going to end up doing here is we're going to convert each clause into a clique of 3 vertices. So here I'll label them x0, x2, and not x3. And I'm going to have them be fully connected. That is what it means to be a clique. What this is going to do, by our constraint of independent set, is now only one of these can be chosen in our subset. Correct? All right. So I'm going to do the same for this. Now I'm going to have not x0, I'm going to have not x2, and I'm going to have x4. Okay, once again, only one element can be chosen from this set. Now, how could I construct this, and what value k could I choose such that this is only going to return a true answer if the original circuit was satisfiable? I want everyone to process the words I said and make sure you understand what I'm asking you. If you don't understand what I'm asking you, that is a missing piece you need. If you don't understand the creative step to get there, that's okay. But hopefully you can come up with something. Yeah.
Connect like X0 to not X0.
So that's definitely a reasonable idea. So we know that in the original constraint here, x0 and x0 not can't both be true. So we can connect them. So these two are connected now. If I choose one, I can't choose the other. Similarly, with x2 and not x2, we connect them. Okay? Now, with that added, is that sufficient? What do we choose as our k? Yes?
Number of columns.
Exactly. So we're going to say, this is going to be our construction. I've just described it verbally. I haven't written an algorithm for it or anything. And then we're going to say that k is going to be equal to n, where n is the number of clauses. And what we realize is that it's only possible for us to choose n elements if I only choose one from each of these. I've already added that constraint. And I have no choice of both x0 and not x0. Okay? And that is for any xi. Okay? Makes sense? And those are exactly the constraints of 3-sat. So now we have that, in fact, this will only return true to this being possible if this algorithm, or if this circuit is satisfiable. And I can get it pretty easily. If I wanted to return the actual satisfiability, I would just see what is chosen in my subset. And I could say that that is an assignment. And anything else that isn't chosen from there, it doesn't matter what I choose. Yes?
So my question is, I can see,
Yeah.
you connected the line.
Well, so I'm not drawing lines to make it an and. I'm connecting x0 to not x0 because they can't both be true. So I'm associating, like my construction is saying, if it is chosen as part of my subset, part of my independent set, then it is true in the original statement. That's how I've constructed it. So I can't have that both of these are true. That makes sense? So I'm drawing this line to add that extra constraint. It does not have to do with the and. If I had another one of these that had no overlapping terms, there would be no lines between it.
So then that's why you
Yeah, exactly. Cool. Any other questions on this? So, yes.
If it was like X0 and X2.
No. So what do you mean by and x2? So I'm connecting only things that can't.
In the first clause.
The first clause can't be an and.
Oh, then it's not.
It's in CNF form. Yeah, exactly. It's in 3 CNF form too, even. So we say that all of these have exactly 3 elements. Yeah. Okay. So the things that we would still need to do to prove that this reduction is true, and in fact that independent set is NP complete, is 1, we need to prove that this construction takes polynomial time only, which it does. You can relatively easily show that. Basically, I'm only going to be adding a vertex for every one of these, which is going to be 3 times the number of clauses, which is not. It's going to be polynomial. Are you gonna? Okay. There is a detail here that I'm skipping, but it's not an important detail, I think, for this. This is a slightly more involved proof. And then we need to show that anytime this returns true, this is true, and anytime this returns false, this is false. Okay? And vice versa, if we prefer. So what I can do first is I can say, if this is true, that means that I've chosen exactly one element from each one of these, and I haven't chosen any pair that are mutually excluded by this, and I can relatively easily prove. I'm not doing the formal proof right now. We don't have time. On reductions, you are expected to do formal proofs, though. Yeah, there's no clock in the room if you're looking. But that will exactly be the satisfying assignment for 3-sat. And we know that if it exists here, then I know that I must be able to satisfy this because a chosen one from each one of these clicks is going to correspond to one of these being true, and if there's one true from each one of these, then in fact it is satisfiable. And vice versa, if it is impossible to do this, it is a little bit more difficult. So there's two ways I could prove this. Either I could show that if this is not possible, then it's not satisfiable, or I can prove that if this is satisfiable, then this would result in a true also. So you get what I'm doing there? So what I'm trying to show is that, I'll write it out here. So if I had independent set, I'll write it as IS, by the way. So I'm saying if IS is true on some arbitrary input, that will imply that 3sat is true. I should write f of a. Sorry. On f of a, this is going to imply that 3sat is true on the original problem. And the other thing that I want to prove, because I want to show that they're equivalent to each other, is that IS, like if this is false on this, then this would prove that 3sat is also false, right? But it turns out sometimes doing it this is more difficult, right? So I'd have to show if it's not possible to do this one, then it's not possible to do this one, and that can sometimes be hard. So we can remember our logic rules and know that this statement right here, this bottom statement, is actually equivalent to 3sat from A implies IS. So we can actually just do we do another positive case, but the reversed implication. That make sense? Okay. So here I can see that if this is possible, that means there must be one item that's chosen from each one of these that don't break this constraint. And so in this problem, I would choose exactly those to be in my subset. Again, there's a bit of a hand-wavy way to do this. Do you have a comment?
Well, you wouldn't select. You'd only select like just one of them in each clause. Like true.
It could be
true
multiple. I can just arbitrarily pick one of them. Yeah. Okay. Yes. S equals to k. So this is the size of set k of sets S, which is going to be some subset of vertices. The size of it, the number of vertices, is equal to k in the subset. And then it's saying that there isn't any edge between any elements that I pick. So when I say independent set, that means no neighbors are chosen in my subset. Make sense? Okay. With this, I think just so that we have enough time for this, I want to turn it over to your quiz, which is going to be another reduction building off of independent set. Or 3sat if you so choose. But 3sat is usually a little bit harder to work out of. You can talk to neighbors now if you'd like to.
You're gonna have to modify. You're gonna have to modify.
I mean, you would know immediately that it's elements are not as high independent set. Has vertex color. Are there cases?
Oh yeah. What if case
Worst case 6.
the D has to be C?
See if you can figure out why they're different. Try that example. And see for what values it pairs each.
I think you have to modify it. Yeah, the ED modifier. I think it's
You need to prove that the answer is correct. You need to be able to prove that the answer is true. That's the majority of ranking. Violence left in class. Finish it very quickly and prove to me that you don't need the time.
Is the complement of the cover I say complement.
Probably somewhere crazy. I was
All right. Anyone got something? Okay. Well, first off, is it in NP? Okay, cool. You can once again, this is another one that's very simple. You just say here's a solution, and then you just need to prove that you can check the solution in polynomial time. That's what a lot of them are going to be. There's occasionally something that's more difficult where you have to be a little bit clever with it, but probably not in this class, to be honest. All right, Ezra. You did from 3SAT. Unnecessarily complicated. All right, cool. It is doable from 3SAT, by the way. It is, I believe, not a known fact if every NP-complete problem can reduce to every other NP-complete problem, but it's very likely true. Do you know if it's true?
Wait, you just changed it.
Oh, no, you can, yeah, because you can say that, you can. You reduce all NP to circuit set, you can do that. But it isn't necessarily going to be a simple one. Anyone have more direct from independent set? Yeah? So this reduction is actually incredibly simple. I know that this isn't an insult to you. You will see that it is incredibly simple. The reduction is just the following. An instance of independent set is some G, which is vertices and edges.